Hi. Okay, thanks for all coming out here. My name's Yoni. I'm going to be talking about a research project that I'm actually working on right now. So this is still in progress and still thinking about it, but it's something that I'm really passionate about, so I'll let you know what I'm thinking about. The title of this talk is Fairness is Not Static, and it's about a deeper understanding of long-term fairness with the ML Fairness Gym. So I guess this lies somewhere at the intersection of fairness and machine learning, if you've heard of that term, and also explainability in a sense. But this is a slightly different notion of explainability, so I'm just going to lead with what I mean by what it means for an AI algorithm to be explainable. I think of different algorithms as explainable if, when I'm given a number of choices, I can understand the consequences of using each of them. So for the purpose of this talk, I'm not going to really refer to how any algorithms actually make their decisions, just what happens if you were to use an algorithm like this to make a decision. There have been a number of algorithmic fairness interventions that have been proposed, probably in the last 2-3 years. It really took off in around 2016. So for example, if these are things you've heard of, like applying equality of opportunity constraints. This is a kind of constrained optimization method to make sure that different groups in your population have equal recall from some classifier. Or debiasing word embedding, so trying to make sure that when you learn word embeddings from texts, you try to make sure that they don't kind of pick up the human biases that are inherent in that text that you're training from. And so I guess when we're thinking about these things, though, we may know what these interventions do, but it's not always clear what the implications of these interventions are kind of in the middle of a system. So will other systems that depend on this system be affected in the way that we actually expect them to? Will users change their behaviors in response to these new learned models and, in fact, kind of change the dynamics of what we're working with? And how will future data collection be impacted by these changes? And if we keep it up for a long time, so if we make this change and then kind of play it forward for a long time, making repeated decisions with these new kind of, let's say, fairer trained models, will they actually have the intended effect? And are there unintended side effects to others that were not targeted by these interventions? I should say that kind of everything I'm working on at this stage is very purely in the research stage. So this will have very little impact on products. The things that I'm talking about today will not have any real implications for products at this time. But these are the questions we're thinking about. So here's an example that was considered in a paper last year called Runaway Feedback Loops and Predictive Policing. Though the issues of predictive policing are kind of more complicated than our simulation captures, but you can think about it as this kind of generic attention allocation problem. So that could apply to any number of scenarios like pest control, health checks, things like that. So you can imagine this toy setting where there are 5 locations in a city, and you can allocate some amount of attention to discover these kind of bad incidents that are happening. And these incidents start out unevenly distributed. So when we observe new incidents, we only observe them in places where attention has been allocated. And maybe our likelihood of observing goes up as we allocate more attention. So you can kind of imagine this system that works like this. And then there might also be some feedback. So more attention may cause incident rates to go up or down. This might depend on the problem being studied, but it could happen in some cases. So what would happen if we did the following things? What if we allocated our attention according to the kind of discovered incidents that we saw in the past? So we looked back over some number of days, tried to count how many incidents we discovered in each of these places, and then allocated our attention according to those counts. That was the setting already kind of described in this original paper, the unsigned et al. Paper, that talks about allocating attention purely according to your observed incidents is a bad idea. This makes this unaccounted for feedback loop, where the observation pattern and the allocation scheme are tied together. And then the place that initially gets more attention then looks like it has more incidents. disparity between the locations grows, and it just doesn't work out right. So this is something we already know. But what if instead of doing that, we use some model to estimate the number of incidents? So we'll use some sort of maximum likelihood estimation or propensity score matching type of things. Would that actually end up working out well? What else could we want to do? We might, and I should say, even this question of what does it mean to work out well over the long term is not fully obvious. So it could mean something like, if an incident happens in location A, is it equally likely to be discovered than if it happens in location B? So this is kind of like this coverage fairness. Or it could be, if I am location A, will I have more incidents going undiscovered than location B? Those two sound like very similar things, but actually the way you would optimize for them are different. So we might just kind of say this all sounds really complicated. We don't know even how to do this, so we'll just allocate attention uniformly. Or maybe we could do some kind of fancy long-term optimization using reinforcement learning to try to maximize discovered incidents overall. And you might kind of see where I'm going with this already. If we're asking these questions, what would happen if I did this or this or this? One way to address that is just to kind of simulate this out and see what happens. So we'll imagine that, actually I should say, we'll simulate this process, but in order to even do that, you have to choose what you're going to measure. So when I started working on this simulation stuff, I kind of thought, well, we'll just simulate it out for 1,000 steps or 100 steps, and then we'll look at the simulation trace, and we'll figure out if it's fair or not. It turns out that I don't know, for me at least, it's an information overload. You end up getting thousands of numbers, you just look at them all, and you're like, I cannot tell if this is fair. So you still need to talk about what you're going to measure when you're working with these simulations and kind of project down that very rich simulated data into some sort of summary statistics. So let's see, what are we going to measure here? The first thing we can look at is the missed incidents in each location. So each dot represents one of 5 locations. Blue is for the uniform allocation scheme, and orange is for this proportional, I think probably using a maximum likelihood estimation model with a small amount of exploration. So this epsilon term is saying sometimes, even if you're doing kind of this modeling process, you still need to kind of look outside of what you've already seen. So sometimes you do some random exploration. It looks like, let me just think. Yeah, I guess if you look at these plots, the proportional allocation scheme actually reduces the number of incidents overall and kind of reduces the spread of incidents, reduces the worst case city of incidents. So it looks like a generally good scheme. So overall, you'd say this proportional looks better than the uniform baseline, you could say. And then you could ask, is this always true? And it turns out it's not always the case. So we're going to now add in this dynamic factor. We'll let this x-axis here, we'll let the number of incidents change in response to attention. So when you put attention to a place on day 1, the number of incidents on day 2 goes down. And if you don't give attention to a place on day 1, then the number of incidents actually grows. So now this proportional model isn't fully modeling the world. It might be modeling kind of today, but it's not modeling the whole kind of scope of the history. I should also say it does end up being also a little bit delayed. So it can only look back. It doesn't actually know today's rate. It knows kind of the average over the last week's rates when it tries to estimate things. And so it can kind of fall behind of the kind of today's rate. And what ends up happening is, in this case, this proportional with epsilon. You can ignore the green for now. It kind of interpolates between the blue and the orange, the uniform and the proportional. But as the problem becomes more dynamic, it actually, in this case, is better to be uniform than to try to do this kind of smart proportional allocation scheme. We should say this isn't because uniform allocation is like optimal in any way. It's just the proportional method gets broken when you add these dynamics into the system. But here's the part that I think is really interesting. So sorry, let me just think for a minute. Here's the part that I think is really interesting, which is like, does the proportional agent even know that it's not being successful? So remember we talked about, on the last slide, we had measured uncaught, missed incidents. But the kind of agents that are doing this problem can't actually see their missed incidents. They can only see the incidents that they caught. So that's kind of this. There was two parts to the simulation. There was this feedback loop, but there was also this observation pattern that can cause trouble. So instead of the plot of missed incidents, we'll look at the plot of discovered incidents. You could imagine that we try to optimize, catch the most incidents that we can. And this is from the same simulations as the last slide, where proportional agent was doing really badly. Here, it actually looks like it's doing really well. When it measures itself on how many incidents it catches, it actually kind of grades itself highly. And what's happening is that the total number of incidents overall is going up because it's kind of missing a lot and going to the wrong places, and then the rates grow. And then, so overall, overall, kind of in our ground truth view, it looks like it's doing worse, but it thinks it's doing better. OK, so what did we learn from this? I guess even with simple dynamics, it can be hard to predict what's going to happen until you try it. That's number one. Number two, you need to think very carefully about the relationship between measurements that are easy and those that you really care about. So in this case, discovered incidents are those measurements that just kind of appear, just kind of come to us really naturally. It's really easy. But it's very easy to misunderstand kind of the partial story by just looking at discovered. By the way, this problem of estimating the number of missed incidents is not impossible. I'll leave this kind of as a general challenge to the crowd to think about how you might do that. It's not impossible, but it would take some extra work. And I think it's worth kind of thinking through what a system that is constantly trying to do that would look like. How are we doing? So we can now kind of move this out to another. So that was the attention allocation kind of problem setting. Another problem we're looking at, this came up from a different paper called The Delayed Impact of Fair Machine Learning. So here there are 7 possible credit scores, 0 through 6. Your probability of repaying a loan depends on your score. Scores are unevenly distributed between groups. Then you only see outcomes for applicants who receive the loans, and unpaid loans cause your credit score to go up. Paid loans cause your credit score to go down. So you could then ask this question, how would you try to act fairly in your handing out of loans in this scenario? This is kind of a scenario that's been discussed in terms of these equality of opportunity constraints, this constrained learning to equalize recall. But there are actually some very strange things that happen. So while that may make sense in kind of the static one-step version of this problem, when you play it out over time, it actually becomes very strange as you try to equalize recall. So a few things that happen. First of all, and this has been noted in the past, in order to equalize recall in this setting, you have to have different thresholds for different groups. That's kind of, well, the profit maximizing threshold will be a single one. In order to equalize recall under different distributions, you would have to have 2 different thresholds. But another thing that's interesting is that in this problem, the kind of optimal equality of opportunity constrained thresholds, let's say, change over time. So at every step, kind of the right threshold, because the population distributions are changing, the kind of right thresholds to both maximize your profit subject to these equality of opportunity constraints changes at every step. So that's kind of strange and may not be expected. As you play it out over time, you're constantly having to change your threshold. Another thing that's strange that I'm pretty sure is true This is something I'm still working on, but it does seem like if you try to satisfy these constraints at every step and then look back and sum over a whole week of loan decisions, so let's say if every day you're applying equality of opportunity, so each group has equal recall as the days go for every day individually, and then you look back and you sum over a week, you find out that it's not fair over the course of a whole week. It's one of these Simpsons paradox types of situations. And so that's kind of this unintuitive notion. It just kind of turns out that this thing that sounds great, this like, oh, we'll do classification subject to some extra constraints, ends up behaving, even though it looks very normal in the one-step process, ends up behaving very strangely in the many-step process. So this is kind of going back to the title of this talk, Fairness is Not Static, thinking about these problems not just as here's a data set, but here is a simulated environment, and trying to play it out over time often helps you understand it better and helps you think through kind of the implications of what you are doing. Third example, maybe I'll skip. Let's talk about this one too. How much time do I have? 15? OK, cool. Perfect. Thanks. Sorry about that. So here's another example that I think is really interesting, where a college publishes some admission criteria score. But then students can either pay a cost either through effort or through money to try to do some work and raise their scores to meet that criteria. But they'll only do that if they expect it to help. So that's kind of this feedback process. Let's say the cost to raise scores is somehow unevenly distributed between groups. And then there's this observation pattern where the college only sees scores after they've been raised and only sees outcomes for the accepted students. So this is a setting called the strategic classification or strategic manipulation setting. There's kind of a standard robust procedure, which is to raise the classification threshold so that it kind of accounts for these students' abilities to raise their grades. But kind of the uneven costs mean that what's called in this paper the social cost of strategic classification, the unequal costs mean that kind of that, you can think of that as a tax on the system, because there's some score manipulation going on. The threshold gets raised in order to account for that, but it ends up falling unequally. Kind of that cost ends up being unequally distributed between groups. An interesting thing about that is that even if the college is not doing this standard strategic classification process, but is just actually acting in response to the scores that it sees. So if you think about it, it sets a threshold, people change their scores, it then learns from that, change their scores if they think it's worth it for them, present those scores, and then it accepts some people, gets some feedback, and learns from that. That kind of process of learning from these manipulated scores ends up being related. So if you play that out over time in kind of this game fashion, you get close to what the strategic classifier would have done in the one-step process. So if you play that over time, your kind of threshold raises naturally because people keep on manipulating the system. And so even, I guess the kind of takeaway here is that, well, this paper talked about if you're applying strategic robust classification, you have to be worried about these unequal costs. It turns out that even if you're applying regular classification, but this process is happening, the over time threshold that you learn kind of looks a lot like the strategic classification threshold. And so this is kind of an interesting process where, as this plays out, the threshold you learn changes at every step and approaches this robust threshold. On the one side, that's kind of cool because you get this robustness property. On the other side, it's kind of scary because you have this social cost getting unequally distributed. OK, so these are kind of 3 different scenarios that have been proposed in papers in the past, and mostly analyzed in a closed form, kind of analytical frameworks. And what we've discovered is that when we simulate them, we actually find out all sorts of interesting things, and it can be really cool. So we put together this simulation framework. If you're familiar with reinforcement learning, this may look super familiar. If you're more used to classification on static data sets, this will look slightly strange. But you can imagine two parties interacting where you have an environment and a learning agent. The environment sends observations at time t to the agent. The agent then gives actions to the environment. And this goes around in a circle. The agent is kind of building up its data set that it's learning from over the course of this simulation, rather than starting with a data set. And what that means is that the agent, in some ways, is more responsible for its data collection than you may kind of be used to. So in kind of traditional supervised machine learning, the machine learning people step in after a data set has already been collected and then start to the formulation is often there exists a data set, you then take it and you do something with it. In this framework, this is often thought of as the reinforcement learning framework, you have much more agency, much more responsibility on the learner to actually think about how it's going to be collecting its data from an environment. What else can I tell you? The last thing that we do is we collect all of our metrics on this from the environment. So this is kind of a very judging things by how they play out, so it's like this very consequentialist notion of fairness compared to thinking about things like how is the agent making its decision or why is the agent making its decision. We kind of ignore all of that and just ask how does it affect, how does it play out in this environment over time. I'll say that by making that choice, we probably don't cover kind of the whole range of philosophical fairness concepts, but I think it's generally interesting in this case. And we've put this online for people to play around with, to contribute with, to kind of view each of these environments, the lending, attention allocation, and college admissions as challenges to kind of ask, can you design a learning agent to act fairly, to kind of have good outcomes in each of these environments? You're welcome to go check it out. This is a very early release, but we're putting it out because we want to kind of engage with the community and see what people can come up with. So that's what I got, and there's time for questions now.